For the last week in this first semester, we are going to talk about, first quarter I should say, we are going to talk about chemical bonding and Lewis structures. A Lewis structure is a way in which we show how the chemical bonds are formed and what happens to the valence electrons. For verily I say unto you, till heaven and earth pass, one jot or one tittle shall in no wise pass from the law, till all be fulfilled. Matthew 5:18. So first of all, let's do a run through at the three most common types of chemical bonds. The first of all, a chemical bond is an attractive force between atoms that is strong enough to enable the group to act as a single unit. And so what happens is there are other attractive forces that occur between atoms and between molecules. But these attractive forces are strong enough that the atoms involved are linked together in such a way that unless some significant action breaks them apart, they will act as a unit or a group on their own. This determines, and can many times determine, the physical state of the matter as well as the shape of the atoms or molecules and properties of the molecules that are formed when these chemical bonds occur. The molecular shapes are very important because these molecular shapes determine other forces between molecules that occur, these being called intermolecular forces. Now, intermolecular forces are not the same as chemical bonds. Chemical bonds occur between atoms and form molecules. Intermolecular forces, inter meaning between the molecules, intermolecular forces are forces between different molecules that occur. So the types of chemical bonds are as follows. First of all, a understanding of the valence electrons is critical in determining the type of bond that will be formed. Valence electrons, in case you don't remember, because I think we've talked about valence electrons before, valence electrons are those outer shell electrons on any particular atom. As I told you when we went through the periodic table, one of the really important parts of the periodic table that you can use the periodic table for is the groups on the periodic table have the same number of valence electrons as the group number. So when you go from group 1A through group 8A, excluding the transitional elements, if you're in a group 1A element, then you have one valence electron. Group 2A elements have two valence electrons. Group 3A elements, such as aluminum, have three. Group 4A, such as carbon and silicon, have four valence electrons. Group 7A, like chlorine and bromine and iodine, have seven valence electrons. The noble gases have eight valence electrons. And this is one of the reasons why elements in a particular group have many times similar physical and chemical properties, is because they have the same number of valence electrons. Elements react in order to achieve 8 electrons in their outer shell. Now, there's rare exceptions to this, but we will probably not encounter any of these rare exceptions in this class. We may encounter them if you take the subsequent chemistry class, but usually I do not use the exceptions as part of this class. Now, the way that elements achieve the rule of octet is they either take electrons from another element, they lose electrons to another element, or the two or more elements will share electrons. And there are different ways that sharing can occur, and so that's what determines the type of chemical bond that we're talking about. The first of these types of bonds is called the ionic bond. Now, in the ionic bond, essentially one element completely gives up its electrons, its valence electrons. And the other atom or element completely takes those electrons. And both elements end up achieving the rule of octet by doing this. So this is a bond where electrons from one atom are totally given away to another atom, and in the end, both atoms have 8 valence electrons. This results in a positively charged ion, known as a cation, and negatively charged ions, known as anions. And this is why these are called ionic bonds. This occurs when there's a significant difference in electronegativity between the two combining elements. Electronegativity is the degree to which a atom wants to hold on to its electrons. You remember we talked about, in periodic trends, we talked about first ionization energy. Well, that's another way of stating electronegativity. If you have a high first ionization energy, if you really want to keep your valence electrons, then you have a high electronegativity. If, on the other hand, you have a low first ionization energy and it's easy for you to lose an electron, then you have a low electronegativity. And when there's two elements that come together, one has a very high electronegativity and the other has a low electronegativity, then they like to be together. One element gives its electrons up freely because of its low electronegativity. The other element takes the electrons freely because of its high electronegativity, and everybody's happy. And you have a nice ionic bond. Now on the periodic table, as I'll show you in a minute, these elements are separated from each other by a significant distance. That means that one element is frequently on the left side of the table and the other element is frequently on the right side of the periodic table. This is also true in the fact that you remember the right-sided elements are frequently nonmetals, the left-sided elements are metals, and so that's why they're far apart from each other. So here's an example of an ionic bond. This is sodium chloride. The purplish balls are sodium ions, which are positively charged. Sodium is if you want to get out your periodic table, you'll see that sodium is in the 1A column, has one valence electron. It has a fairly low electronegativity. And then the chlorine is a 7A element on the left or right side of the table. It has a fairly high electronegativity. So the sodium willingly gives up one electron to the chlorine. The sodium then has 8 valence electrons from the shell underneath that one electron. So it has the same electron configuration now as neon, which is in the 8 column. And chlorine, gaining an electron, also has 8 electrons in its outer shell. So both are very happy now. And then the gaining and losing an electron causes that ionic forces, which are what causes the opposite forces to attract each other, and they then arrange in this lattice structure, which is shown on the left or on the right here under B. And so the atoms in sodium chloride are arranged to maximize these opposite charges interacting. The smaller spheres, which are purple, represent the sodium ions. The larger ones represent chlorine. The expanded view on the left, on the right, shows the geometry and shows why these are crystalline structures. So each sodium is surrounded by 6 chlorides and each chloride is surrounded by 6 sodiums. So here's what happens. You start out on the left here, you start out in the picture above, you have 2 atoms that are separate from each other. You have a single electron on the outside of the sodium here, and you have 7 electrons on the outside of the chlorine. This one electron is easily removed and moves over here, so now you have 8 here and these 8 here, which is shown down here. And so you have a positively charged sodium and a negatively charged chlorine ion. Now, what this shows is that you have the relationship in the periodic table, and here's sodium on the periodic table here. It's a metal and it's far on the left here. And here's chlorine on the periodic table. It's on the right. It has a high electronegativity over here and a low electronegativity over here. Now this just shows some other examples. We had sodium chloride here. I don't like the word electropositive. It's better to say it's a low electronegativity rather than electropositive. I don't like that word. But what you can see here is, for example, rubidium is also a 1A element over here, has 1 electron, and fluorine is a 7A element, and so that will form a fairly significant ionic bond. But here you have chlorine and oxygen. They're both nonmetals. They're fairly close together, so their electronegativities are fairly close together, and they form a covalent bond. Now I'm not going to talk about hydrogen chloride here because hydrogen is unique in the fact that it's over here on the 1A side, but it actually has an intermediate electronegativity, and so it frequently forms covalent bonds with nonmetals, and it really doesn't act like a metal like the rest of these over in this area. Now, ionically bonded compounds frequently form a crystalline solid at room temperature, and then they commonly have a fairly high boiling point and a fairly high melting point. So what that means is that the ionic bonding between atoms is fairly strong and does not allow for that to be broken apart very easily, and it's very difficult to break these apart. So it takes a lot of heat in order to melt the solid and also in order to achieve boiling. When the solids are molten, they conduct electricity. Now, when they're not molten, the electrons get bound up in the lattice, and so a block of sodium chloride does not conduct electricity. But if you melt it so that the ions are floating around free, then the electrons will pass through fairly easily. Another way is if you dissolve it in a solvent like water, it will also cause electricity to flow pretty freely. As I just said, most ionic compounds will dissolve in polar solvents, and I'll explain what the term polar means in a minute. But water is an example of a polar solvent. And when it is dissolved, then electricity is conducted through that solvent pretty easily. And as water is aqueous solutions of ionic compounds will conduct electricity. On the other hand, if you have a nonpolar solvent like benzene, the ionic materials will frequently not dissolve in that. And the best example of this is oil and water, to the difference between a polar solvent and a nonpolar solvent. The oil being a nonpolar solvent and the water being a polar solvent. Those two, as you well know if you've ever done anything with oil and water, those two things do not mix together well. The second type of bond is a covalent bond. In a covalent bond, the transfer of electrons is not absolute. Remember, in ionic bonding, there was a transfer of electrons from one atom to the other, and that was permanent and absolute. In this case, 2 or more electrons are shared in such a way as to get the requisite 8 electrons to fulfill the rule of octet. So what that means is that 2 or more atoms come together, and they will share with each other electrons so that each of those atoms at one time or another has 8 electrons in its outer shell. The electrons are shared almost always in pairs, And the sharing can be equal, which is what is meant by a nonpolar bond, because there's equal sharing between the two, or the sharing can be unequal, which causes what we call a polar bond. Now, the reason it's polar is because whichever of the two has the electrons for a longer period of time will have a negative pole, and the other side, which has the electrons for less time, will be positively charged. Similar electronegativity is usually seen in two atoms that combine. Now remember, with the ionic bond, you had to have different electronegativity for the bonding to occur. With covalent bonding, you have similar electronegativity. And this is almost always when two nonmetals combine with each other.